This video is an introduction to equilibrium, focusing mostly on the equilibrium constant. So I just want to clarify, again, using a reaction energy diagram shown at the bottom, that we've been talking about kinetics, how fast a reaction goes. And again, that's just determined primarily by the activation energy for the reaction. And equilibrium tells us how much product versus reactant we have. In other words, how far does the reaction go to completion? That's equilibrium. And that is determined more by delta G here, or the total energy change involved in the reaction, and tells us nothing about speed. Many reactions are reversible. It really depends in large part on the difference in energy between the reactants and products. Notice that sometimes you're going to see the difference in energy just represented by enthalpy. They're leaving out the entropy, so that's not the whole story. That's just a common way to present reaction diagrams, and sometimes you'll see it as delta G, the free energy. I just didn't want that to confuse you. They both give related but slightly different pieces of information. But a reversible reaction is necessary to have equilibrium. Okay, equilibrium is really a balancing act between reactants and products. And so in order to have that balancing react, the kind of back and forth, it needs to be a reversible reaction. So a reminder, equilibrium is dynamic. In other words, when you reach equilibrium, you can no longer observe any changes in the amounts of products and reactants. It looks like it's stopped, but it has not stopped, okay? That's why it's called dynamic equilibrium. A very common misconception that students make is they think equilibrium sounds like something's equal, right? It does not mean that reactants and products are equal, okay? So try to strike that out of your head right now. That may be a coincidence, but it's almost never the case. What is equal is that the rate of the forward reaction equals the rate of the reverse reaction. And when that happens, you have reached equilibrium. I mentioned briefly on the last slide that a reaction needs to be reversible and that it depends in large part on the change in energy between reactants and products. I wanted to show you a visual of reaction that is reversible and one that is not. So look at the situation, the graph on the left. The activation energy going in the forward direction is really reasonably small, so it's easy to achieve. But once you form the product in this reaction, look at the activation energy going in the reverse direction. Okay, that is really high, okay? So once you form product, they're not going to tend to want to go in the reverse direction. It's like falling down into a deep hole. It's much harder to get out. So this, for all practical purposes, is not reversible. On the other hand, when the difference in energy between the reactants and products is pretty small, it's much easier for the reactant to go forward and reverse. And equilibrium will be reached quite rapidly in this case. All right, again, we're still just kind of reviewing the definition of equilibrium. On a large scale, there's no visible change when you've reached equilibrium, but on a molecular scale, the forward and reverse reactions are continuing to go nonstop. The position of an equilibrium, or the extent of a reaction, is measured quantitatively using an equilibrium constant. It is a capital K. Be careful to show it as an uppercase capital K, because remember that lowercase k is rate constant, two completely different things. And so the actual mathematical expression for an equilibrium constant, that's the primary theme of this video, so you want to make sure you understand this, is represented by this equation. So look carefully at the generic reaction shown here and make sure you understand how we get from that reaction equation to this form of the equilibrium constant. Notice that products, the concentration of products are on top, and the concentration of reactants are on bottom, okay? Which means the more products you form, the larger K will be, right? So a large equilibrium constant is good for chemists. It means, okay, I've made a lot of products compared to how many reactants I started with. The other thing I want you to notice in this equation is that the coefficients in the balanced reaction become exponents in the equilibrium constant expression. Now this is where it gets massively confusing for a lot of students, so listen to what I'm getting ready to say for a moment. When you are working with rate constants, the rate of a reaction, remember that those exponents represent the order of reaction, and the only way we can determine the order of a reaction is through experimentation. So with kinetics, you are not allowed to use these coefficients as exponents. In equilibrium, you have to, all right? So that's a really, really important distinction. You do not have to be able to derive the equilibrium constant, but it's kind of interesting and very simple how it came about. Remember that the rate of a reaction, the rate law, has this form: rate constant times the concentration of the reactants. And equilibrium is defined as when the rate of the forward reaction equals the rate of the reverse reaction. And so if we set up this rate law equality and rearrange it, we get the equilibrium constant, which is just kind of cool. All right, very important here. We're going to do some practice writing equilibrium constant expressions, but I want to point out that if a substance is a pure liquid or a solid, and you'll be able to tell, well, some of them you'll probably know, but you'll be able to tell by the phase notation in the balanced equation, they are not included in the equilibrium expression, and that's because the concentration of liquids and solids remains constant. So just as an example, water in its liquid form has a concentration of 55.5 molar. That's not going to change in a chemical reaction. So the concentrations for liquids and solids are just lumped into the expression or into the value of the equilibrium constant K and left out of the right side of the equation. All right, so for example, let's say that I gave you this balanced chemical equation and I asked you to write an equilibrium constant expression. Remember that it is products over reactants. So let's look at the products first. Okay, we have water as one of our products. Hopefully you remember that, okay, water in its liquid form has a constant concentration, so that does not belong in the expression. However, anything that's aqueous can change its concentration, so that does in fact belong in the equilibrium constant expression. There is a coefficient of 1 in front of calcium ion, so the exponent is simply 1. Moving on to the products. Calcium hydroxide is a solid, so it does not go into the equilibrium expression. And again, hydrogen ion, aqueous, does. So hydrogen ion goes in the denominator, as all reactants do. Now pay close attention. There is a coefficient of 2 in front of this hydrogen ion, so that becomes an exponent. you do have, just a reminder, you have go formative questions to give yourself some more practice while you're listening to this. KEQ, or the equilibrium constant, is very useful to chemists because it gives them an idea of how far a reaction will proceed. You're probably used to so far, especially in the lab, when you do a reaction, it pretty much proceeds totally to completion. You get all product. So there are ways that chemists can manipulate a reaction to kind of force it to completion, but if just left to its own, most reactions, reversible reactions, will form a certain amount of product and then stop unless pushed, which we'll talk about later. So there are tables published of equilibrium constants at certain temperatures for different reactions. And if it is a small value of the equilibrium constant, that means there is not very much product, okay? Small k means the numerator is small, not very much product, and that's not good for chemists, right? They want product, so that's a good piece of information. If it's a large equilibrium constant, we would say that it's product favored. A lot of product is made compared to how much reactant was started with. I kind of like this diagram on the bottom here. So it just lets you visualize this. A small equilibrium constant, so it's something less than 1, will have a lot of reactants and not very much product. And a large equilibrium constant will have just the opposite, a lot of product. You do have some equilibrium constants kind of in the middle, where you have roughly equal amounts of reactant and product. All right, so now how do you know if you're at equilibrium? If you're a chemist and you're running a reaction, how do you know if you've reached equilibrium or if the reaction is still progressing? Obviously, you can monitor concentrations and wait until they don't change, but depending on the time scale, what if a reaction takes minutes versus hours versus days? How do you know if it really has stopped or not? Well, you can use something. I shouldn't have said stopped. A reaction never stops. Equilibrium, it keeps going back and forth. It appears to have stopped. Okay, you can use something called the reaction quotient, Q, capital Q, to tell you for sure whether or not you're at equilibrium. So the expression for the reaction quotient is identical to the expression for the equilibrium constant. However, the reaction quotient K is taken at any time in a reaction, okay? So you can calculate Q in the beginning of a reaction and every so often. And what you're going to do then is you're going to calculate the value of Q at any point in the reaction, and you're going to compare it to the known value of K for that reaction. Obviously, if Q equals K, you're at equilibrium. You're done. If it's not, if Q does not equal K, that means you are not yet at equilibrium. Now, what gets just a little bit more tricky is if Q is less than K, you're on one side of the equilibrium. If Q is greater than K, you're on the other side. So it's likely you're going to be presented a problem like that and asked, which direction must this reaction shift in order to reach equilibrium? So I'm going to show you how to go about doing that. My favorite way to compare Q and K, and I think by far the easiest, is to make a quick number line and place Q and K on the number line. So, for example, if Q is less than K and you use the number line, Q is going to be to the left of K, right? Assuming the number line starts at 0 and then goes larger, right, as normal. So what you do then is you always start your arrow at Q. And whatever direction you have to go with your arrow to go from Q to K is the direction the reaction must shift. So if Q is less than K, the reaction must shift to the right in order to reach equilibrium. So on the other hand, if Q is greater than K and you make up your number line, you can see now that Q is going to be to the right of K on the number line. And again, always starting at Q, what direction does Q have to move to reach K? In this case, it has to move to the left towards reactants. All right, so that may take a little bit of practice on your part, but that's an important concept. An interesting property of equilibrium, I think, is that regardless of the concentrations of reactant and product that you start with, so you can see down here in this table, we start with all different amounts of reactant and product. Regardless, the equilibrium constant or the final ratio of product to reactant is the same. That's cool, isn't it? So regardless of how much product and reactant you start with, you're going to end up with the same proportion of product to reactant at a particular temperature. Now, I want to point out, and I'll say this over and over and over, equilibrium constant K is a constant only as long as temperature is a constant. The only thing that can change the value of K is the temperature. That's really important to remember. I've seen a lot of trick questions out there that try to suggest that K changes for all different reasons. It does not, only temperature. So in this particular reaction, we've talked about this one before. This is the formation of smog, very dependent on temperature. So get in the habit of writing the equilibrium constant expression or reaction quotient expression, same thing. Okay, so it's nitrogen dioxide squared divided by the concentration of N2O4. You can prove this to yourself if you want. I have a feeling you're not going to want to. But equilibrium concentrations, now the only concentrations that belong if you're calculating K are the equilibrium concentrations, right? If you're calculating Q, you can use any old concentration you want. And the second column is based on the initial concentrations. And again, once the value for the reaction quotient Q equals the given value for the equilibrium constant K, you are at equilibrium. You may remember this graph I presented early on when I think I first mentioned equilibrium. When you plot concentration of reactants and products versus time, when the ratio of the product to the reactant is constant, okay, when there's no more change in the ratio of the two, you have reached equilibrium. All right, so there are some ways to calculate or obtain an equilibrium constant for a reaction by using other equilibrium constants that are known. Let's just say you're a chemist, you're running a reaction, there is no published value for equilibrium constant yet. You can figure it out indirectly if there are related K values, equilibrium constants, for similar reactions. So let's look at what the heck I'm talking about. Example, if you have two reactions that add together to give you a third reaction, so let's just say A plus B equals C, and then C plus D equals E. So you should know by now how to add reactions together, right? Hess's law and all. So the overall reaction, A plus B plus D gives E, is a result of adding these two reactions together. So the K, or the equilibrium expression for this overall reaction, would equal the product of the K's for the reactions you added, okay? So if we call this reaction 1, call this reaction 2, and call the bottom one reaction 3, we could say that K3 equals K1 times K2. Here's an example for you. If we have this overall reaction, nitrogen monoxide reacting with bromine to give NOBr, and let's say we need the equilibrium constant for this reaction, but we can't find it published, but we know when we add these other two reactions together that we get the overall reaction we want. So I'll just rewrite it here. So after we cross out the intermediates, we end up with the overall reaction we're looking for. Yay. So we can take the published equilibrium values of these reactions we added together and multiply those equilibrium constant values to give us the equilibrium constant for this reaction. That would probably be a multiple choice type question on your next exam. All right, so other ways you can manipulate K. Let's say that we had that same reaction, and for whatever reason you want to present that in a different balanced format. So what did we do to get from the top chemical equation to the bottom? We divided by 2, right? So anytime you multiply the coefficients in a balanced equation, that means that multiplicative factor, I think I just made up a word, becomes an exponent in the equilibrium constant. So it really needs to be in terms of multiplication. So instead of saying divided by 2, I'm going to say, okay, multiply by 1/2. Same thing, right? So what do we do then? Notice that the equilibrium constant for the first chemical equation is given here. After I have multiplied that equation by a factor of 1/2, all the coefficients, the new equilibrium constant is that original one raised to the power of 1/2. So whatever the multiplicative factor is becomes an exponent in your K. Now, just to kind of remind you, if you raise something to the power of 1/2, that is the same thing as taking the square root. Just makes it easier on your calculator. All right, and a final way that you can manipulate chemical equations and equilibrium constants, if you have a reaction, let's just say A goes to B, and you reverse that reaction, so that would mean products become reactants, reactants become products. If that's the case, what you do to the equilibrium constant is you change it to 1 over that equilibrium constant when you reverse a reaction. So to put specific numbers in, if the forward reaction has an equilibrium constant of 261, what would be the equilibrium constant of the reverse reaction? It would be, how did I suddenly change that to 262? It would be 1 over 261, which is about 3.83 times 10 to the minus 3. Now, one thing that may be obvious, but I just kind of want to prompt your brain cells to absorb it. If the forward reaction favors product, the reverse reaction will favor reactant. So let's write it out in typical equilibrium format. All right, we have a reversible reaction. The forward reaction, if the forward reaction has a large K, which means it favors product, right? So you're going to have more of B. That means, by simple math, the reverse reaction, now you call B, in the reverse reaction, B is called the reactant, right? So in the reverse reaction, you're going to have a small K, which means that reactants are favored. Now keep in mind, when we're talking about the reverse reaction, the original product becomes the reactant. Okay, so hopefully that didn't confuse you. We're closing in on the end. All right, so here's a couple examples for you, and remember, again, there are go-formative questions to answer. Let's say I'm starting with this reaction, and we're going to call its equilibrium constant just equal the some number R, okay? What would be the equilibrium constant for reaction number 2? That should be kind of easy for you. So what have we done to get from number 1 to number 2? We have multiplied by 2. All of the coefficients have been multiplied by 2. What else have we done? We have reversed that reaction, right? SO2 and O2 were reactants in number 1. They're products in number 2. So we've done 2 things to this reaction. Let's go ahead and manipulate K one at a time. I'm going to do the reversal first. So the original equilibrium constant was R. When I reverse the reaction, it becomes 1 over R. But now I've also multiplied all the coefficients by 2. So the final change to K is 1 over R squared. Here is a nice summary slide of all the manipulations you can do with the equilibrium constant K. So the top reaction is just your reference. In other words, no manipulations have been made. Again, if you reverse the reaction, K and Q are now 1 over the original K. If you add together different reactions, what you need to do to the equilibrium constant is, or Q, either one, is multiply the K values that you added for the reactions you added. And what's in the middle here is just a derivation. You don't need to be able to do that. It just kind of shows you where that comes from mathematically. If you multiply the coefficients in a reaction by some factor, that factor becomes an exponent in the value for K. And just a reminder to leave pure solids and pure liquids out of the expression for both Q and K. 2 more slides. Real quickly, we've talked about K in terms of concentrations. So products over reactants, right? Now, they can also be in terms of pressure if the reactants and products are gases, or if you have even one gas as a reactant or product, you can monitor that reaction in terms of an equilibrium constant in pressure. There is a mathematical equation that relates the value of equilibrium constant with respect to pressure and compares that to the value for the equilibrium constant in terms of concentrations or molarities. And this is it. So this is an equation you need to know. R, as always, that universal gas constant shows up everywhere, doesn't it? And the value of the universal gas constant we always use is one that matches the units of the other variables in the reaction. And in this case, it would be 0.0821 liters atmospheres over mole Kelvin. That tells us right there that temperature must be in Kelvin, right? We want to match all the units. Delta N is somewhat the tricky part in this equation. That is the difference in the moles of gas that are on the product side of the equation and the mole of gas that are on the reactant side of the equation. So I'm going to show you a specific example to show you what I mean. That's the part that can trick students up sometimes. All right, last slide here. Let's look at this equation. And how many moles of gas do we have on the product side? We have 2. How many total moles of gas do we have on the reactant side? We have 2 plus 1, or 3. So delta N, it's always moles of the product side minus moles of the reactant side. So in this case, delta N, the exponent in our expression, is minus 1. Now, here's an important thing to keep in mind. If the number of moles of gas are the same on both the product side and the equal side, reactant side, that means that delta N would be 0, right? And in which case, if you look back at this math equation, if delta N is 0, anything raised to the 0 power is 1, right? So in that case, what happens? Kp has the exact same value as Kc. I recommend your exam is in exactly 1 week. It's time to start working hard. There's a lot of challenging material, kinetics and equilibrium, so I recommend working quite a few problems. That's it for this PowerPoint.